All right. Well, last unit, those were two-dimensional figures. This unit, three-dimensional figures. So we got prisms, cylinders, pyramids, cones, and a sphere. This unit, three-dimensional objects. If you want to impress somebody at the cafeteria table today or dinner tonight, these are called polyhedrons, those three-dimensional figures. All right, polyhedrons. Every polyhedron has faces, edges, and vertices. So take a look at my cube here in number 1. The faces are the sides. So can you count up real quickly how many faces that cube has? And it has 6 faces, yes. All right, so I'm just going to jot right underneath F equals 6 for faces. They also contain edges. Edges are the sides of the faces. Those are the segments right now that make up the faces. So if you want real quickly again, go ahead and count. See if you can figure out how many edges are on there. Do we have an agreement on how many edges are on this cube? It should have been 12 edges you counted. Yep. And finally, they all have vertices, which is the endpoints of the edges. That's where 2 edges meet, is a vertice. Okay. So can we have all an agreement how many vertices where the edges meet? I am getting 8 vertices as well. All right, well, I think we can all be in agreement. Sometimes you may miss a vertice or an edge. Sometimes you may count it twice. Is there a way to check that I have the correct amount of faces, edges, and vertices? You're darn right there is. Back in, and this is a true story, I'm not joking around with this one. Back in the 1760s, there was a mathematician by the name of Leonard Euler. Let me say that again, Leonard Euler. And I guess he had some free time on his hands, and he did the faces, edges, and vertices for a ton of polyhedrons. And he noticed a pattern. Every single one had the following pattern. The number of faces plus the number of vertices minus the number of edges, always 2. Always came out to 2. No matter the figure. Always come out to be 2. And take a look. That works for our cube, doesn't it? 6 faces, 8 vertices, that's 14, minus the 12 edges, 2. Works every time. So if you're nervous, maybe I missed a vertice or I double counted one, try to put it into Mr. Leonard Euler's formula to see if you're correct. All right, I'm going to give you a minute. You by yourself or with your group, numbers 2 and 3. How many faces, edges, and vertices for me? And if you're nervous, see if it fits into his formula.
Minus 9 is 2, really. 11.
All right. Let's go to, anybody know what this is, first of all? We'll be dealing with them on Monday. Pyramid, yes, pyramid. Those are pyramid. That is a pyramid. Here we go. Let's start it off right. 27. Here we go. How many faces? 5. How many edges? 8. How many vertices? There we go. And then if you check, that does fit into Euler's formula. Nice job. 6. Anybody know what we call this? A prism, triangular prism. Anybody know why I call it a triangular prism versus anything else? The bases, which we'll get into in a second, are triangles. All right. Here you go. 10. What do you got for me? How many faces? 5 faces. Edges? 9. And vertices? 6. And that would also fit into Euler's formula. All right. Any questions from you guys there? Faces, edges, vertices? All right. Next thing. Cross sections. How to do a cross section. Here's the deal with cross section. I'm going to take a polyhedron. All right. In this case, I have a rectangular cylinder here. All right. I'm going to take a plane. I am going to slice the polyhedron. I'm going to take it apart and show you what's left. The figure that's left, the shape that is left is the cross section. So let's say I took my rectangular prism here, did a vertical slice, held it up, what figure would it be? It would be a rectangle. Everyone agrees? It would be a rectangle. Yes? No? Okay. Same thing here. Let's say I do now, instead of a vertical, let's say I do a horizontal slice. And I hold it up, it's still going to be a rectangle. Okay. Let's get a little deeper then. I had it up there. It was working first period. Ready to go. There we go. All right. Now I got a cylinder. Take a look. Now I did a horizontal cut. What's my cross section? It's a circle. What happens if I do a vertical one? Rectangle. Okay? Rectangle. Now, let's see if we really got this down. Let me go back to my rectangular prism. And as we said before, horizontal cut makes a rectangle, and a vertical one also makes a rectangle. Do you think there's any other shape other than a rectangle I could get as a cross section? And remember, it doesn't have to be vertical, horizontal. I can cut it any way, any angle. Do you think I can get another figure other than a rectangle out of that? What do you think? It's going to maybe take me a while here. Triangle. All right, if I sliced it kind of off the corner there, you could get a triangle. So I don't want you guys just assume it's always a rectangle in a rectangular prism. Okay? Everyone good there? Everyone all right on the concept of cross section? Because we got a couple questions right now. All right, here you go. So for this first example, which figure can have the same cross section as a sphere? So we've all seen a sphere before. Hey, here you go. Spheres. I don't care literally how you slice it. Always going to be what? A circle. So what I'm asking in this problem here is, what other figure could I get a cross section that results in a circle? Which one where I could cut it in a certain angle where I'd also get a circle? And that would be a what up here? A cone. Yes, if I do a horizontal slice of a cone, that would be a circle. Here's what I want you, don't yell anything out. Here's what I want you to talk about in your groups. Here's a cone. Which cross section could I never get from a cone? So think about all the ways to cut a cone at all the different angles. Which one would I never get as a cross section? Okay, ready? Well, obviously circle. Up. Little, I don't know really what to call that, the little arch there. You can get that if I cut it diagonally. Everyone see that? And then finally, if I go just straight vertical, what do I get? A triangle. I can never get a what out of this? A square. Yeah, I can never get one out of there. All right, so that's why it's going to be number 1. We're all good. All right, here's the big meat of today, Monday, Tuesday, first half of this unit. Lateral area of a figure versus the surface area. Have we ever heard of those terms first? So I get a little background from you. Lateral versus surface area. Yes, no? Okay. Let's take that prism I have up there already. All right. There are 2 bases to this prism. Anybody want to tell me the shape of the bases for that prism up on top? Pentagons. Well, first of all, how'd you know those were the bases and not the rectangles? How'd you know those were the bases? Okay, so how do I know what the bases are of any prism? There's 2 of them. They're parallel to each other and congruent. Are there any rectangles in that prism that are parallel and congruent to each other? No. There's only 2 figures that are parallel and congruent, and those are the darn pentagons. Okay, so those are the bases. So first, let's discuss what lateral area is. Ready? Guys, take those pentagons off. Take them off. Take them off the figure. What's left over? Some rectangles. The area of all those rectangles is the lateral area. The lateral area of the figure is the area without the bases. All right, so here's what I'm going to put here. It's going to be the sum of the faces. We're going to go a little rhyme time here. Sum of the faces without the bases. So if you are asked for lateral area, you need to visually take those bases off, find the area of what's left, which is probably going to be rectangles for us. Surface area, now what do you think? It's everything. Everything. Put the bases back on. So this is the sum of all faces. I'm not going to write that, but sum of all the faces. Surface area is everything. Lateral area, everything without the bases. All right, we're ready to get after it now. Get those calculators fired up. Let's go. Here we go. Two jobs, not one job, 2 jobs. Lateral area, surface area. All right, right away we run into a problem. First problem, there's an issue. If I want to do lateral area, you guys know from the last part, you got to take the bases off. Oh boy, where are the bases up there? Because there's a ton of sides that are parallel and congruent to each other. Oh, because look, you could, right now you could say, all right, base, top, and bottom. So here's the base, the bottom, there's the base. But what if I turn it 90 degrees? Now these 2 bad boys are the bases, right? So we are going to follow the following rule. When we deal with a rectangular prism, everyone ready? When we deal with a rectangular prism, we are going to consider the bases as the top and bottom as it's drawn for us. All right? So for instance here, as it's drawn, the top and the bottom, we're going to consider this as the top base, and then the one at the bottom here as the bottom base. As it's drawn. Everyone good there? As it's drawn. So everyone right now, take them off. Take them off, because we're going to do lateral area now. Take them off. First, let's do this front face. What are the dimensions of this front face? It's a rectangle. We know from last unit, length times width. What is it for the front face? 10 times 3. And isn't there one in the back too? That's congruent to it. So I'm just going to multiply that by 2. Everyone, take a look at what I have up here. We okay where this is coming from? This represents the front and the back face. Plus, we got 2 on the sides, right? What are the dimensions of the 2 on the side? 3 by 3, and there's 2 of them. 2 3 times 3. Am I missing anything else? For the lateral area anyway. Remember, I don't want to count the bases. I think we're good, yes? Okay, so lateral area. Five, what do you got for me? Bless you.
48.
Do you even have to pry it? Hey, this is lateral. Wait, where'd the 48 come from? Where's 48 coming from? Considering 3 times 10 times 2 is 60.
Oh, I meant 78. Sorry.
Oh, you meant 78, yeah. All right, going back to my comment there. This is lateral, lateral. One more time, lateral. So it's still square units because we're dealing with area, yes. All right, surface area. Guys, most of the work is done. You already know 78 is the lateral area. Now what are we going to add on? The 2 congruent bases. So 2 congruent bases, what are the dimensions of them? 10 by 3. And the surface area, 1 meg. Honors kids, can we just, one quick discussion here about common sense. Anybody know anything about the surface area compared to the lateral area should be true every single time? Surface area should be bigger, yeah. Okay, so if it's not, something did go wrong. You don't need to raise your hand and say, what happened here? All right, something went wrong. All right, surface area should be bigger. All right, number 2, here we go. Now, ready? What are the bases here? Triangles. They're the only 2 that are parallel and congruent. Take them off right now. What's left over? 3 rectangles. So the lateral area will be the area of the 3 rectangles added together. So take off the triangles. Okay, let's do the one that's on the floor there. What about the one on the bottom? What's the dimensions of the rectangle on the bottom? 12 by 16. Plus, let's do the one to the left right here. Let's do the one to the left. That looks like, what's the dimensions of that one? 9 by 16. Everyone's good. I haven't lost anybody yet because I saved this one for last. Plus this one to the right, which looks to me to be 16 by, how about that bet? I don't know that length. Right? I don't know that length. Okay, we're in week 35 right now. I think we have a way to find the length. 21, thoughts? Set it up. There we go. So yes, some of the times it's not convenient and just won't be given to you. And what are you finding for that other dimension? 17. 15? Thank you. So the lateral area. Meg, up to you again. Lateral area. Thank you. And then now surface area. Here we go. I'm going to do this slow. This is new to many of you. Surface area. Well, I already did the lateral area, 576. Plus, what were the shapes of the bases? Triangles. Go back to last unit. What was the formula for a triangle? 1/2 base times height. How many of them are there? 2, 1/2. And I know when I'm in an honors class, and some of you are thinking right now, do I need to do the 2 and the 1/2? And the answer is no. It's going to come out to be 1, but I'm just showing everything here. So everyone good. 2 triangles, with the formula 1/2 base times height? What are the base and the height of these two right triangular bases? 13, what are the base and the height? 12 times 9. Because as we know, the base and the height of a right triangle are the two legs. Finish this strong right now. 684 square inches. There we go. All good, guys, with the prisms before we go on to a new one. Here we go. Cylinder. I would like you, with my help, for you guys to come up with the formula on your own. Here we go. Cylinder. What's lateral area again? Everything but the... Okay, boom, they're gone. Bases are gone. I'm just left with this right here. No bases. Ready? I unfold the cylinder. What's it become? What's the area formula for a rectangle? Length times width, right? Let me go back to my cylinder. This side right here, the rectangle, is also known as the what for the cylinder? The height. Everyone agrees this right here is the height of the cylinder. So we're going to have height in our lateral area. Okay, so we're going to have something times height. What? Ready? Let's go back. I want to know what this part now of the rectangle represents. That's called the circumference. Go back 2 units. What was the formula for circumference? What was it? Pi. Why am I hearing a squared in there? Pi d. So let's put them together. The lateral area of a cylinder. Pi dh. Pi dh. That is not on your formula sheet. I'll just let you know that. That's not on the formula sheet. And then surface area. I think you could come up with that one on your own. What are you going to put on this now? What are you going to put on the pi dh? 2 circles, right, as their bases. So you got the lateral area, pi dh. What was the formula for a circle last unit? But how many of them do you have now? 2 pi r squared for the surface area. All good. Okay, real quickly, let's go through some of these basic ones, and then we'll get to this last question, which I'm going to love tremendously. All right, lateral area of each cylinder. We just found out the formula, pi dh. Let's hear from 21. What's the diameter here? 10. Okay, now look, guys, I get it. You're just going to plug in 2 for the height because that's the other number there. All right, I want to make this clear. Stop writing. Stop writing. Stop writing. All right, because it's not going to be clear in some problems what the height is. The height of a cylinder, listen, the height of the cylinder is always find the 2 bases, and it's the distance between those 2 bases. Okay, let me say that one last time. The height of a cylinder is the distance between 2 of the bases. All right, so find both circles, find the distance between them. In this case, yes, it is 2. I'm going to ask, you're going to find that comes in handy, maybe not today, but sooner or later. And then round it to the nearest 10th. What do we have? 62.888 centimeters squared. And then we have lateral area for this one. What's my diameter for this cylinder, number 4? 6, height of 6 as well. Everyone see that? Distance between the bases. And then this one will come out to be, what do we got? 113.1 square meters. Looking all right? And finally, now let's turn our attention to surface area. But directions. In terms of pi, have a pi in your answer. So pi dh plus 2 pi r squared. I need somebody to help me fill in all the pieces here. 9, you're up. Fill in the pieces for me. Diameter. Height. Radius. There we go. So what do we have here? 6 pi plus 2 pi? Can you combine them? Can you combine those two? Do they both have pi's? Okay. If you have 6 pi and I give you 2 more, you have a total of 8 pi meters squared. Yes, indeed. Yes, indeed. And then 6. I need somebody to fill in the values for me. 24. Let's roll. Not here. Why do I even do that? It's like every class has a number that's numbers. 1. Meg, you're on fire today. Pi d h plus 2 pi r squared. $70 pi plus 24.5 pi. Yes, we can combine them to make 94.5 pi centimeters squared. Ladies and gentlemen, that was basic. Basic. You want to knock it up to an honors level? Here's where you got to be. Here's where we have to be. And we are going to get one of these. A couple things. This is how we're going to end class throughout this unit, is with one of these figures. When you get it on homework, we don't skip it. Okay, we don't skip it on homework. And by the way, speaking of the homework this unit, you will see that it's minimum. Like, I think, what do you have, 5 tonight? Out of the book anyway, 5. And I think it's 4 on Monday. So the homework is very minimal this unit. I'm scaling way back. All right. All right, let's get to this one. A figure on top of another figure. And it's find the surface area. So as we know from today, surface area is just everything, right? Everything. We got to make that a little more detailed now. Ready? Everything that is showing. We're just not going to do cylinder plus cube, add them up, we're good to go. We can't. Is everything showing on the cube? No, everyone see, you got that little circular part on top that's covered. I can't count that towards the surface area. Is all of the cylinder showing? No, one of its bases is covered up. The surface area of a figure is everything that is showing on the outside. Everything I can glide my hand over. All right, that's the surface area. So we need to come up with a way of, hey, I want to do the surface area of the cube, but I can't count that. I want to do the surface area of the cylinder, but I can't count that base. Then we can add them together. You want to start with the cube or the cylinder? Cylinder. How many cubes do I have in the house? Cubes? First? Okay. Cylinders? Okay. Now, guys, listen. I'm going to do this one way, and you may start, cranking the gears in your mind and say, well, what about, couldn't I do that? And it might work. Try it out. See if we come out with the same values. All right, so don't knock my way. All right, if you have another version of doing this and getting the job done, that's fine. I'm all about it. All right, cylinder. Usually, it's pi dh plus 2 pi r squared, right? Usually. But what do you know about one of the bases? It's going to be covered up. So I'm not going to put plus 2 pi r squared, am I? What's it going to be? Just plus pi r squared. Just please ask, is everyone all right? Why? That base is being covered up. You cannot count it as the surface area if it's covered up. All right, let's figure this one out. So I have pi. What's the diameter? 4. Height of the cylinder. Distance between the two circles. 4 plus pi. What's the radius? 2 squared. Ask away here. We good? All right, let's keep going. Let's see. That's 16 pi. That's 4 pi. For now, I'm just going to leave it as 20 pi. If you guys want to go an extra step on me and write out the full decimal display on your calculator, go ahead. But I'm going to stop there at 20 pi. You ready for the cube? Everyone ready for the cube? How many full faces of the cube are showing? 5, and they're all the same dimensions. So I'm going to start this out by saying 5 times what are the dimensions of the 5 full faces that are showing? 5 by 5. So I'm going to start right there. Now we got to talk about the 6th face, the one that the cylinder is on. How can I figure out what's showing on that one? So I got the 5 full faces here, plus how can I come up with some type of numbers here that'll tell me this part that's left over on the top? Skim, what do you got back there? Happy birthday, by the way. Are you going to go clubbing with the boys this weekend to celebrate? All right, good. Get it going. Don't get too crazy. So basically, you want me to add, ready? 25, right? Which is the area of that face, minus pi r squared. Everyone see that? Minus the area of the circle right now. So minus pi. What's the radius, Teddy? 2 squared. Everyone see where we're getting that from? Again, one way. Some of you may be doing it a different way right now. Great. So I get 125 here. What do I get here? Plus 25 minus 4 pi. So I'll write out the full decimal here. So I have 125 plus 25 minus 4 pi. Here's what I'm getting. I'm getting that area to be of the cube that's showing 137.4336294. Everyone okay? Ask away, guys. You're going to have one of these tonight. Everyone's all right on the cube, and we are not skipping it. And then what do I do with these two areas now? Add them together. There are no directions, so we're just going to go all the calculator display. And if we add that to 20 pi, we're getting 200.2654825 inches squared. That's how we're going to end class every day, but as we start building on the figures, it'll get a little bit more sophisticated, the diagram. Anything from you guys there? Going. Regents, pack it out. Here we go. Regents, pack it out. 27. 27 on your own or within your group. 27 should look pretty familiar. $27. Oh, look at you. Bless you, bless you. I think we have this one. What type of angle did we refer to CFE as? What name did we give that type of angle? CFE. 8, remember the name we gave it?
Angle CFE. Oh, that's a floater angle?
Floater angle, got it. How do I do floater angles? Did I add or subtract the arcs? Add them. So I'm going to do 1/2. What arc belongs to CFE? So it's going to be 1/2 of CE plus what's its vertical angles arc? DB. So I'm going to do 1/2. Oh, wait a second. I didn't give you CE. How could you find arc CE though pretty quickly? Hi, Meg. Correct.
And since we have arc DB, you can find directions.
180 minus 46, 100 and 134. DB was already 102. Bless you, bless you. The angle ended up being 2. 118 degrees. Any issues with that one? What? That would be if the angle was on the outside. All right, so if I start pulling one of these here and I try to find angle P, that's going to be this arc minus this arc divided by 2. Okay? Had nothing to do with the party hat, but she's asking about an angle. Questions? All right, do not give up on the 2-figure one tonight.